Okay, great. So good morning. Oops. Good morning and happy Monday. Hope you had a great weekend. Today, we will finish up our discussion, everything I had to say on the continuous distributions. And we're going to be focusing today on the normal distribution, which is by far, I won't say the most important, but it's very important, particularly because it has many applications in interface with the real world. A lot of physical phenomena are governed or well defined by the normal or so-called Gaussian distribution. But before we begin, the usual administrative bits. So the reading has not changed. Again, the reading deadline is there to help you with pacing. As of today, we have, 4 weeks or 3 weeks and 2 days worth of class. We will finish up this module this week and then spend the remaining 3 weeks talking about machine learning methods and implementations of APIs of them in the scikit-learn package in Python for the extraction of insights. And so project number 5 has been out. It's the easiest project of the semester. Thought I'd give you a little bit of a break, and its purpose is to demonstrate to you that this idea of obtaining enough, quote unquote, enough samples allows you to produce estimates through statistics. These estimates are good replacements for these unknown population parameters. And for that, I'll stress one more time that for this exercise, you're going to know what those ground truth population parameters are, but in real life, in real situations, you don't have access to them. In order for you to see that your estimates from the data approach the population parameters, you have to see what the population parameters are to demonstrate that. Any questions? Yes. Yes, it'll be the classic regression. We'll do classification, we'll do clustering, we'll look at ensemble methods, we'll look at information theoretic methods, and then if time permits, maybe neural networks, but it depends on how our pacing goes. So yes, it'll include regression. Okay. And to do that, I'll have to kind of give a very high level whirlwind about linear algebra, because to do that regression, you need something called least squares projection, and you need matrix inversion in order to do that. But I won't hold you responsible for linear algebra, just make you aware of what it is. And you won't be actually, calculating the linear algebraic constructs, but it's just to show you this idea of cumulative loss, which we'll talk about when the time is right. Okay? All right. Any other questions? No? All right. And so after today, that's an old note. We have 4 weeks left after today. So we're kind of past the midway point, and before you know it, summer will be upon us, or at least a summer break will be upon us. But just since I'm on the topic, anyone of summer, is everyone looking for internships over summer or here and there? All right. So one of the things to consider when you look for internships, and I tell my advisees this, is to, kind of try out different parts of the country if you're willing to travel. The computer science, data science hotspots, and by hotspot, I mean there are many more jobs than there are people, and therefore more opportunities, are Washington, D.C. area. That's like Baltimore, Maryland, Virginia, greater D.C. area, Silicon Valley, Boston, and New York City. And so if you're willing to spend a summer in any of those places, certainly try to target any kind of data science internship. Also consider the small companies, not just the large companies. These startups, small, like 20 people, to medium size, about 500 people. They're always looking for interns. And the benefit I found in a small company, spent part of my career working in a startup, early in my career, they foist all sorts of responsibility on you because they can't afford not to, because they have fewer people for what they're trying to accomplish. There's a nice website called builtinboston.com. which is exclusive to all these small startups in the Boston startup ecosystem, and many of them are looking for interns. And just try for it. The most they can say is no, right? So try for many, and you only need a few handful of yeses for great opportunities. Okay, so that being said, let's continue on where we left off. So when we left off, we talked about this idea of uncountably infinite, the set of real numbers. And we said this type of infinite is so big that you can't even identify the individual elements. If I were to tell you what's the next real number to follow 1.1, you might say 1.11. No, or is it 1.00001? And because of this problem, the probability associated with an individual real number is zero because we have one unit of probability mass. And if you try to divide that among these uncountably infinite possibilities, it's going to be zero because one upon a big number is always zero. And so the solution for fixing those probabilities was, instead of looking at probability mass associated with a single element of the real numbers over which these probabilities are defined, you look at intervals or spans along which this probability is defined. And so we use the analogy, as we have on the slide, of having a notion of one unit of peanut butter. It doesn't matter if it's a tablespoon or a cup. Well, I don't think any recipe, well, maybe a cake, but anyways, one unit of peanut butter, and you spread this peanut butter along a span of bread, and that's what this horizontal axis is supposed to be. And what this cumulative distribution function, or CDF, talks about is how much of that total unit of peanut butter is spread over some segment of bread. Now, before, I had talked about using the integral between negative infinity and positive infinity, but that wasn't entirely correct. For the CDF, for a particular value, in our case, it'd be a particular real number, what you talk about is how much of this unit of peanut butter is spread from minus infinity up to that particular real value. Does that make sense? Okay. And so that's going to be some number between 0 and 1. And the derivative, the first derivative of the CDF, is the so-called density function. And what that density function defines is how thickly spread that peanut butter is, the thickness, if you will, along some region of the span of bread along which you spread it, or more formally, along the regions of the support set over which this density is defined. Okay, any questions? Does that make sense? Yeah. And so when we talk about this, you might wonder, well, what do we do for something like the gamma distribution that traffics in time? Well, time cannot be negative. So for that particular distribution, we find that its value for the density, let me grab my pen here, its value, and I'll pick dark blue, its value, here's 0. Oh, that's a bad color. Let me do this. Let's try that again. How about black? Here's 0. And everything to the left going towards negative infinity. For the gamma distribution, this is defined as 0, right? And so for any type of continuous distribution, its density function says it's 0 amount thick for a particular set of values along your span of bread or your support set. And so does that make sense? Any questions? Yeah. And so if you were to compute the CDF, well, you would just take your expression for the integral and you would break it apart for the first part of the integral, going from minus infinity to 0, our density function dx, and then you'd add that to the other part where it is defined from 0 to x, our density function or thickness dx. Okay. And in the standard statistics course, you would certainly learn to compute these CDFs from something called the moment generating function, which will tie into hopefully module 20, which I hope to at least start today. Okay. Any questions? No? Make sense? All right. So I just want to make sure to be more specific in correcting that record. All right. So where we last left off, we talked about the gamma distribution. And we said this gamma distribution it well defines a so-called algorithmic or multi-stage execution. And this corresponds to any type of system that traffics in time, and it consists of alpha many steps, each one of which takes some time, where time is modeled as our exponential, which is governed by parameter lambda. And so a gamma is the concatenation or the sequencing of alpha many exponentials. And so when you talk about a gamma distribution, what you are getting out of it is some probability that the entire alpha step process is going to take a time called x. And so you might ask, well, why don't I just use a single exponential? The reason for that is that these individual components have some variability, each of these alpha many steps, and you're much more fine-grained in your representation if you represent each one of the steps. Okay, does that make sense? Any questions? No? So when we looked at the summary statistics, the mean and the variance of the gamma distribution, now certainly in this class, I won't hold you responsible for the derivation. There are several derivations floating out there, and I think I might have posted the gamma. I can't remember my own videos, but this stuff is, over 100 years old. There are very many sources that give you these derivations if that's something of interest to you. And so the population mean, mu, of a gamma distributed random variable is alpha upon lambda. And we made the observation that 1 upon lambda looks familiar. It's exactly the population mean, mu, of the exponential. And so this gamma, that alpha, is just the sequencing of alpha many exponentials. So we have 1 upon alpha plus 1 upon alpha added to itself alpha many times, and we get alpha upon lambda. All right, does that make sense? Any questions? In similar fashion, the variance is just the sum of the variances of the individual alpha many sequences of this exponential. And so for similar reason, we get 1 upon lambda squared plus 1 upon lambda squared added to itself alpha many times for a result of alpha upon lambda squared. Okay. Any questions? No? Make sense? All right. And so you'd use integration by parts if you were to do this out yourself, both for the variance as well as for the expectation. So let's continue on to our last continuous distribution that we will look at in this class. Let me hide the meeting controls. The so-called normal or Gaussian distribution is very, very important and has a lot of broad application because it's a good model for describing quantities that are physical quantities, things you encounter in the real world. That could be aspects of light, of pressure, temperature, heat, you name it, the normal distribution applies. Now, these quantities are special in that not only are they physical, you can sample them in your interface to the real world, they're also inertial, right? And by inertial, what I mean by that is that the future state is determined by the current state. If you were to represent or measure my position, and you had, for example, a number line, position 0, position 1, position 2, etc., at one instant in time, if I were to take a step, I don't mysteriously end up on the opposite end of the room. Now, if I were able to do that, you'd all be freaked out, right? That's not how physical world is supposed to work. And so any inertial quantity is one for which the future state in the immediate future is equal to the current state plus or minus some epsilon, right? And that's how physical systems work. So this is well defined by the normal distribution, and here's the density function of the normal or Gaussian distribution. I'll use them as synonyms. It's 1 upon radical 2 pi sigma squared, e to the minus 1 upon 2 sigma squared times quantity x minus mu squared. Okay. And so if you were to plot out the Gaussian distribution, it looks like the classic bell curve. And how this function works, we start out with a very thin spreading of peanut butter towards negative infinity, or in that direction. On the left-hand side, it starts to increase, reaches a maximum, and then experiences an exponential decay. And so functionally, if we look at it, we see that we have here a leading coefficient on the front, 1 upon radical 2 pi sigma squared. And in the beginning, this exponential contribution is small. We get this increase. And then as we go further to the right, the exponent is negative. It's a decay that takes over in the value of the function until it peters out to a very thin spreading of our proverbial peanut butter. Okay. Any questions? Does that make sense? Okay. And so we have the parameters that govern this distribution. The mean, mu, is the notional center of this distribution. It's sometimes called the quote unquote location parameter. And then the variance describes the dispersion, the population variance, and the square root of that is standard deviation. That's sometimes called the scale parameter. And so the higher the scale, the higher the standard deviation, therefore the higher the variance. This thing is going to be flatter, but it's going to be more dispersed. If our mean mu is negative, it's going to shift to the left, your left. If it's more positive, it's going to shift to the right. Now, this is the so-called single variate case. You can absolutely have a multivariate case, which is a Gaussian or normal distribution for instantiations of vectors. We're not going to cover that. I highly encourage you, if you want to do data science interfacing with real world phenomena and real data, I highly encourage you to take a graduate level course in statistics, and certainly to take a linear algebra course, because you need that linear algebra, the multivariate version of probability, in order to traffic in things like the multivariate Gaussian. And so instead of variance, you talk about covariance matrix. And so you need those frameworks to do that. But in this class, we're going to talk about the single variable version of our distributions. Okay. Any questions? Does that make sense? Yeah. All right. And so it's called the bell curve. This is the Liberty Bell and Liberty Bell Center in Philadelphia. If you've never been, it's a nice place to go. See some of the artifacts surrounding the formation of the U.S., also downtown Boston, lots of stuff. But it's called the bell curve because it's shaped like a bell. Go figure. Okay. So that's my little historical moment. So why is this Gaussian so important? This normal distribution, as I said, it is a very good model for so-called physical phenomena. That includes things like position, angle, velocity. And in robotics, we use this normal distribution quite often. And because you can take measurements, if you know those measurements are well defined by a normal distribution, now you can use that normal distribution and ask it for measurements in the absence of actual measurements. So what this means is that you can now use it to predict what the future value of something might be. And so in this example, we have a classic controls problem called the inverted pendulum. If you've ever seen, do you know the Segway vehicle? No? It's like this, or these, what do you call them, hoverboards? It's the same thing. It's called the inverted pendulum problem because it's like taking, like you took a broomstick and try to balance it. It's modeled in terms of the forces and the positions and the velocity as a pendulum that's upside down, okay? And so with that, you take your physical model of what the motion of the pendulum is, and then you take actual measurements. How do I release the pen? There we go. And then you take actual measurements of the position and the velocity and the angle of this inverted pendulum. Then you can predict where it is in a future state, and then turn on your motors to counteract that, to try to get it back to the zero position if it's leaning over too much. And so you end up getting these robotic applications that are kind of unicycle models where they balance on their own, and they can also respond well to disturbances if you try to push it over while it's trying to balance. And so this is a classic controls problem, and the primary model in use here is a normal distribution. You have a normal distribution for the angle of that pendulum. You have a normal distribution for the velocity in which it falls and how it moves. And you can now use that normal distribution, update its mean and its variance based on sensor measurements, and use that to predict where it's going to be at some time instant into the future, and counteract that with your motors before you have the actual measurements. So this normal distribution is very, very important. and it's widely used, at least in robotics, as well as other disciplines. And so another place it's used is in autonomous navigation for autonomous cars or self-driving cars. And it's used in something called the linear Gaussian process. It's just the use of a normal distribution that's updated by measurements along with a model. Position equals velocity times time, similar for acceleration. And you use that representation to try to predict where the position and what the velocity is for your vehicle. And then when you get actual sensor measurements, regardless of the source of that sensor measurements, you can use those actual measurements to then update what the mean is, what your estimate of the mean is, and what your variance is, and take actions with your vehicle based on that model. And so you have typically what's called a motion model, and those are just based on mechanics, physics, about where it'll be at some future state. But in the real world, things are not always so clean. Just because you tell your car to drive, it doesn't mean the wheels are going to move the car at the velocity you desire, because you can get some wheel slip. Friction is a real thing. So rather than have to model all those intricate details about what happens with so-called rolling friction, you use a probabilistic model. And then when you get new measurements, you update what your understanding is of your position by updating the mean and the variance for those distributions representing things like your position, your velocity, as well as your steering angle. And so then once you do that, you have your quote unquote estimate. You can then sample from it and say, hey, tell me where you think you are, how fast you think I'm going. And then when you get sensor measurements from multiple sources, you can then update what those statistics are. Does that make sense? Any questions? And now sensors have error. They're not perfect. And the primary two sensors for navigation of autonomous cars or self-driving cars are LiDAR and radar. Radar is based on electromagnetic energy, and it reflects off of primarily solid objects in the environment. And it's very, very precise in measuring velocity as well as direction in which that velocity is going. It gives you a vector, but it's not very precise on specific distance measurements. LiDAR, and this is the radar here on the right, LiDAR emits laser pulses so many times per second. It could be 10 times a second, could be 100 times a second. And the modern LiDARs, they spin on a turret at some characteristic rate, and they emit these pulses as it spins, and it measures the reflection of the laser light off of objects in the environment, the so-called laser return. And so it can give you direction, not as fine-grained as radar, but it's very good at giving you very precise distance measurements. And so you can take each of these quantities from the radar and from the LiDAR and continually update what the mean or average distance is, what the average velocity is, and use that to get very precise sense of how fast you're moving, the direction you're moving, as well as the obstacles that are around you. And all of that affords itself from our normal distribution. Does that make sense? Any questions? And so if I haven't convinced you, hopefully I have, that this normal distribution is immensely useful, in particular when you are trafficking in data quantities that are measured from the real world. Okay. And it's called a Kalman filter, someone's last name, or sometimes it's called in the literature a linear Gaussian process. Okay. And so a normal distribution is also used for so-called hypothesis testing. There's a special version of the normal distribution called the standard normal distribution, and we'll talk about that, where you can take any normally distributed variable or quantity, and you can transform it to an equivalent normal distribution that has a mean of 0 and has a standard deviation and therefore a variance of 1. And so this is used for this idea of testing what measurement is typical. And if you know what measurement is typical, for a system, you can now detect abnormal behavior. And that's immensely useful. Thought I tripped. Immensely useful for what's called hypothesis testing, which is just the rejection of atypical measurements. So you warm up your system, you take a bunch of measurements, you measure the sample mean, you measure the sample variance, get the standard deviation, and then you test measurements against this relationship between the total probability mass that falls within certain ranges of your mean for your distribution. And so if you go in the negative direction, one standard deviation, and in the positive direction, one standard deviation above and below your mean, for the standard normal, about 68% of your total probability mass falls within that region. And so in statistics, 95% is what's considered as something guaranteed, right? And so if you take your new measurements, you test that against that 95% region of your probability distribution. Now you can say, hey, this is an atypical distance measure. I'm going to reject that because it's not typical of what I should be measuring for my distance measurements at the moment. Does that make sense? And so how is that useful? Suppose you're driving along autonomously and a gust of wind comes along and a bunch of leaves fall in the roadway in front of your vehicle. Now, to your sensor package, it's not going to know that's not an obstacle you should care about. It's going to be momentary, it's going to be transient, but it's going to pick it up. And that might be something that's atypical because all of a sudden, out of nowhere, something just appears really close to you. Do you tell your car to jam on the brakes? No, that might not be the best thing to do. And so this idea of outlier detection allows you to reject new measurements based on this idea of, hey, this is atypical based on the measurements that I usually accept. Does that make sense? Any questions? And so this normal distribution, hopefully I've convinced you now, is very, very useful for all sorts of general applications above and beyond just things that interface with the physical world. Okay. And so an example, some research I did at my previous institution with an undergrad, and her specialty was not computer science. It was well, it wasn't machine learning. It was cybersecurity. And it was based on physical therapy. And so this is just to show you an application of the types of things you can do with the things that we learn in data science. And again, I'm stressing I'm a machine learning researcher, not particularly a data science researcher. What the two overlap, but I digress. Anyways, so when you get physical therapy, and I hope you are never in a situation where you need physical therapy, but one of the practices in physical therapy is to establish where you are with some particular use of your body. And so let's say, something happens, maybe you need knee surgery, maybe you tear your MCL or ACL, tendons or ligaments and things, like meniscus, whatever, and you find yourself having to learn how to walk again. And so they first look at your so-called baseline, what you're able to do, and then they have you go through a series of progressive exercises, and they measure where your baseline goes, what your improvement is. Now, of course, unless you're, Oprah or, Annabelle Johnson, the head of Fidelity Investments, or someone like that, most people with health insurance can't afford to have a therapist follow you around every day. And of course, for most of us, maybe one of you, my arm isn't monetized for some team to hundreds of millions of dollars, right? So for most normal people, you have maybe 6 weeks worth of physical therapy, might come in once a week, might come in twice a week. And so to establish that baseline, they take measurements. And the goal of the project was to use an automated system to record data to effectively implement what we called physical therapist in a box. And so here, this physical therapist in a box project, and this was an undergrad project that I'm hoping to resurrect here. I have all the equipment I brought with me, is that what if we could use motion capture, inertial measurement units, to effectively instrument some patient who is recovering from some pathology affecting the use of his or her body. And then we effectively collect these measurements and do outlier detection. Now, if you notice that perhaps his or her gait is atypical, you can record the context, things like the time, the measurements, what happened going up to that. And so this idea of physical therapist in a box would arm your care team with a type of information to be able to ask the question, what happened at 2 o'clock in the afternoon, right? And so we took a piece of equipment from a company called XSense and their wireless motion capture, and this is what an instrumented subject looks like. And as you move, it records the position and velocity of each one of those little orange boxes, and it sits in little pockets in what is like neoprene, kind of less like the material that a wetsuit for scuba is made from. And so we designed a series of experiments where we attached, or by Velcro, these wooden blocks in the shape of a shoe to the bottom of a shoe. And in regular increments, we changed the height of 1 foot to impact how the person was walking. And so with that, we wanted to know models for quantifying what normality means, and at what point with specificity for the perturbation can we detect these outliers and record the context. And so we had other sensors, not just the mocap system. We had things for respiration, we had things for core temperature, we had things for pulse, etc. Okay, any questions? No? And so for this, the interface design, there was a happy face when things are normal. There was a neutral face for things that were kind of approaching a bad situation, and an unhappy face when it encountered outliers in the gait. Okay, and so this is an example of some of the software, and these plots here that you see going across the screen, those are actual tracks, and we take the motion of each one of these sensors and input that to a skeletal model to actually look at how the joints are moving over time. And we can both animate a skeleton as well as talk about the velocity and the position and the acceleration of each one of the major limbs for the entire body. For this experiment, we only instrumented from the core down. So that's the waist, that's the thigh, that's the shin, and the instep. Okay, any questions? And so this is temporal data. And for this, we had a sliding window capturing samples, and some of the experimental controls concerned whether these partitioned the temporal sequences or whether these temporal sequences were overlapping in various ways. And for that, the consideration was specificity versus computational speed. For the partitioning of time, non-overlapping, you got speed. And for the overlapping by K-1 measurements in the window, you had a better granularity. And for each one of these windows of measurements, we were doing this outlier detection by transforming our normal distribution for each one of these measures to our standard normal that we just talked about. Okay, any questions? No? So lots of interesting stuff. And I hope in this class, that's one of my goals for the design of this class, to give you the tools to enable you to do exactly something like this. Okay. And so it's a density function, and I don't remember why I have this slide here. I think this is an extra piece of the slide. I wasn't expecting this there. I don't remember why I have the slide here. It was probably a good reason. But so using our normal distribution, we take our window of measurements and we do outlier detection. And we update just like we talked about before. Okay, and so we alluded to this standard normal distribution, and I'll just repeat here the normal distribution. And of course, it has the mean mu and the variance sigma squared, and these are the population versions. Now, for the population versions, that's very different from the sample versions. And what you'll see in project number 5 is that you're going to get to see what the ground truth population versions are. So you can calculate the population mean and the population variance. Then you're going to sample from them, pretending that you didn't get to see the population quantities. You're going to compute the sample mean, sample variance, and compute the mass function or density, and then compare them as the sample size grows. But that being the case, this is our normal distribution. And we ask ourselves a question, what happens if we change the location parameter? Okay, So here we have the typical bell curve, and its quote unquote location, its central tendency, is about the mean. And if we subtract mu from each one of our measurements of, say, temperature or position, something interesting happens. You'll notice here the origin axis, this y-axis, this vertical axis, it shifts. Because if you subtract off from every measurement you have, whatever the mean is, a sample mean, that changes the location. You're shifting the location. You haven't changed the shape of the distribution. It's still the same bell curve, but just its central tendency has moved. And you can move it anywhere you want on the number line on the horizontal axis. Does that make sense? Any questions? No? All right. And so if you can do that, well, after you've shifted your distribution, you make your population mean now 0. And in the literature, they'll use the word centered about origin. You're recentering your normal distribution by changing the measurements themselves. That's one type of transformation you can make. Okay. Now, what happens if you change the standard deviation? And you might say, gosh, well, Holness, how do you change the standard deviation? That's a great question. You can take each one of your measurements and you can measure the standard deviation for your entire set of measurements. And then you can multiply each one by 1 upon the standard deviation. That's another transformation. So you can have an additive or subtractive operation to transform your data, and you can have a multiplicative or division, special case, transformation on your data. Now, when you do this multiplication by 1 upon the standard deviation, the sample standard deviation also works if it's the population, but you don't know the population. You change the variance. That variance becomes 1. And if the variance is 1, the standard deviation, which is square root of the variance, also becomes 1. And so when you do these transformations, your normal distribution now becomes what's called a standard normal distribution. Does that make sense? Any questions? No? All right. And so we begin with a normally distributed random variable x, and it has a mean, population mean of mu, and it has a population variance of sigma squared here. So that's mean, mu, variance of sigma squared. When you produce that transformation of subtracting the mean from each measurement and multiplying by 1 upon the standard deviation, the resulting distribution is a new normal distribution, but its mean, mu, is 0, and its its variance becomes 1. And so that version of the normal distribution is given a new name, sometimes called the Z distribution. And this Z distribution is nothing more than the so-called standard normal distribution. And so if we start with some variable x, and it could be the temperature, it could be position, like we saw with the inverted pendulum problem, it could be velocity, like we would have with an autonomous car. If we take each one of our measurements, x, and we subtract from it an estimator for the mean that centers our distribution about origin, and then we multiply the result of this operation by 1 upon sigma, our standard deviation, that's now the z-score associated with that original measurement. And so a z-score is nothing more than the z-transformed version of that individual measurement. So for every original x, temperature, velocity, position, you have an equivalent transformed version, the so-called z-score. Does that make sense? Any questions? No? Conversely, you can translate in the other direction. If you have the z-score, okay, you just multiply that z-score by the standard deviation, and then you add to that the mean mu, and that gives you back this x. So you can map from your original representation, x, to the z version, the z-score, or you can go back in the other direction. Does that make sense? Okay. Now you might ask, well, why in the world would I even care about mapping things to this standard normal or the z distribution? We already talked about this idea of outlier detection. Yeah, but I wasn't entirely truthful. you can actually do this outlier detection as the original normal distribution. So why do we care about this z distribution? And I remember taking a stats course and saying, why do we care about this z distribution? And so, yes, you can do outlier detection, as we talked about before. But the interesting part about the z distribution is that I can take any normal distribution and it preserves the relative probabilities between any measurement, but it shrinks it down to the standard the same way that percentages did for proportions. And so if I said I had a portfolio and this portfolio increased from a value of 100 to 125 versus I had a portfolio of $400 and I said its value increased from 400 to 500, well, if you said which one had a bigger increase, they both had a 25% increase. Now, yes, absolutely, the bigger portfolio increased by $100. The smaller portfolio increased by $25. In order to make that fair comparison, you had to register them on the same scale, right? And that's what percentages did for proportions. For distributions, the standard normal does that same thing. And so the really important part about the standard normal distribution is that it allows you to make fair comparisons between two different normal distributions. Now, when we talk about the central limit theorem, it gets even better. The central limit theorem says it doesn't matter what distribution you are. You could be a Poisson, you could be exponential, you could be a normal, you could be any distribution. And if you apply this transformation, and I'll talk about what that is, you can turn any distribution into a normal distribution. So if you have something like customer arrivals, which is a Poisson, if you have something like temperature, which is normal, how do you compare the two? Well, you can't. First thing you do is you transform that Poisson to a normal, making use of the central limit theorem, and then you turn both of those normals, once you've transformed the Poisson, into a standard normal, and now you can make comparisons. Comparisons like, what is the correlation? What is the linkage? Before you have these tools, you couldn't do that because you can't compare two things that aren't of the same distribution. Does that make sense? Any questions? Okay, so that's why the standard normal is really important. And so, oh, I jumped ahead. Think about what percentages did for proportions. It allows you to compare two systems, even if their scale and their type is very different. And so here, let's say you have temperatures in one geographic location. Temperatures are different. As we see today, our temperature started out, at least where I live, 26 degrees in the morning, and then it goes all the way up to 56 degrees in the afternoon. You can have different types of variability. So if you want to compare one geographic location with another, you transform it to the standard normal, and this is just a representation of that. And then you take the other and transform it to a standard normal. Now you can make fair comparisons. It preserves the relative proportion when you convert to z-scores. And because they're both from standard normals, you can measure things like correlation, look at percentiles, and all sorts of things like that in order to ascertain things like, did the increase, was it the same? It was 25% using that portfolio example. Okay, any questions? Does that make sense? Yeah? No? No? Okay. So let's look at this last one, the central limit theorem, and let's consider any random variable. This is both the discrete as well as the continuous, which is the absolute beauty behind the central limit theorem. And let's say we have some variable, and to pronounce what this squiggle looks like, some variable is distributed as one of our stylized forms of stochasticity, one of our distributions. We've talked about a bunch of them: the Bernoulli, the binomial, the geometric, the negative binomial, the Poisson, the exponential, the gamma, and now the normal distribution. And so it doesn't matter how these variables are distributed as, or if we want to be more casual, how the peanut butter is spread over the bread, right? And so numerous operations that we can calculate from measurements involve the sum of n of them. When we take the sample mean, well, there's a sum involved. Take the first measurement, the second, the third, like we saw with physical therapists in a box, and we multiply each of those measurements, those n many, by 1 upon n. And so let's define the sum arbitrarily of n many measurements as this Sn. And it doesn't matter what n is, and we'll talk about a desirable one, but at this juncture, it doesn't matter what n is. When we compute the sample mean, we make the assumption that each one of the n many measurements is equiprobable. And so we multiply each term in the sum by 1 upon n. If we expand this out, we get a leading 1 upon n, but we still have a sum involved in this particular operation. Does that make sense? Any questions? And it's important to have a sum. And if we were to measure for that sum, the variance, if we have the variance of some sum, Sn, that's equal to the variance of the first measurement plus ... plus the nth measurement. Okay. Now there's a property of variance that says if we have the variance of the sum, that's the same as the sum of the variances. That's precisely equal to the variance of the first measurement plus ... the variance of the nth measurement. Okay. So if that's the case, if we have our expectation or our sample mean, that's just x1 plus xn, and we take each one and we multiply by 1 upon n. Okay. Now, if we take the variance of that sum, we have n copies of this variance in the numerator. So we have n times the variance on the individual ones for the sum. And then if we had this 1 upon n, well, the variance of a scalar is the square of that scalar. And that has to do with the definition of variance involving, for the continuous case, it's integral. For the discrete case, it's sum. We have x minus e of x quantity squared. And so if we have a scalar times this x, it comes out that scalar is squared because of that square term in the variance. Okay. Does that make sense? All right. So here, if we have the variance of the sum, that's just n times the variance of the variable itself. And let's assume this variable had a population variance. We'll just give it a name, sigma squared. Okay. Likewise, if we took the expectation of the sum, well, the expectation, E, of some sum of n many terms is just the expectation. We expand out x1 plus ... xn. Expectation has the same property. If you have the expectation of a sum, that's just the sum of the expectations. So we have E of x1 plus ... E of our xn. Okay, so that's just if the expectation of a single one, if it's from the same distribution, each of these measurements, the expectation is mu, right? The population one. We have that n many copies added to one another. So that's times n times mu. Does that make sense? All right. Any questions? All right. So now we said that we have a sum, but we didn't limit how many terms are in that sum. So what happens then if we let n, the number of terms in our sum, go to infinity? Well, we have a leading n term here. We have a leading n term here. If n goes to infinity, it gets really, really big, countably, then these diverge. They become infinite. Well, that's not very useful, all right? Well, let's think of a different thing. Let's take that sum and let's divide by n, okay? Well, again, the variance of the sum part is n times sigma squared. And we have this 1 upon n. Take the variance of that squares, so it's 1 upon n squared. Now we have sigma squared upon n for the variance of your sum divided by a scalar, which is exactly what the sample mean is. All right. Well, what happens with the expectation of this sum divided by some value, n, the number of measurements? Well, we said that the expectation of the sum is n times the expectation of the individuals. The expectation of a scalar, 1 upon n, is just 1 upon n. The two n's cancel, and we're left with the expectation of the value, which is just mu, okay? So if the number of terms of this sum gets big, well, something interesting happens. This variance goes to 0, all right? And this expectation, it has no impact on. Now, what does it mean to have a variance of 0? Well, for the Gaussian distribution, we have 0 here. Let's call 0 here. Let's say if this is minus infinity on that side, plus infinity on that side, you have what's called a point distribution. A point distribution has all of the probability mass of 1, at a single value, and that value is 0, right? That's what it means to have a 0 variance. And so, well, that's a little bit more well-behaved. It's not infinite like we had before. Let's do something a little bit different. Instead of taking the average, let's take what I'll call the root average. Instead of dividing by n, the number of measurements, we'll divide by radical n, the square root of the number of measurements. So if we do that, okay, our variance becomes sigma squared, all right, of that transformation on our sum of values, and many of them, and our expectation becomes n times mu. Oh, wait a minute. If that's the case, and we started out with this distribution, it acts just like a normal distribution, where for that normal distribution, we have a defined variance that's an actual concrete value. It doesn't go to 0. It doesn't go to infinity, and we have a defined expectation. And so, in fact, anytime you have any variable, regardless of its distribution, and you perform a transformation, the quote unquote right transformation, it acts just like a normal distribution, regardless of what the original distribution is. So, and we'll have an exercise on Wednesday with this to actually show you that this works. It doesn't matter if it's Bernoulli, binomial, geometric, negative binomial, Poisson, gamma, exponential. If you have the right transformation involving a sum, as long as that sum has a large enough number of terms, you can get it to look like a normal distribution. And that's what the central limit theorem says at a high level. Does that make sense? And if yes. Mm-hmm. Mm-hmm. Ah, so n, so s, thank you for asking, is just the number of terms, right? N is the number of terms. And so there's a property of expectation called linearity of expectation. And what it says is if I have a variable x and I multiply that x by some scalar, some number a, that's equal to a times the expectation of what x should have been. And if I look at what expectation is defined as, expectation in the discrete case, right, e of x is equal to the sum, x, the value, times the probability of x. So if I said, what is the expectation of some value a times my random variable x, everywhere I see x, I say a times x. I still have times probability of x. Now the property of summation, I can factor out this common a, and that gives me a times my summation of x, p of x. And so I make the observation that this sum, that's just e of x, right? And so I'm left with a times e of x. That's called linearity of expectation. Does that make sense? And so I'm using that fact, e of the sum divided by radical n is just the same as saying e of x 1 over radical n times x1 plus xn. And so I'm using that linearity of expectation to factor out this 1 over radical n. And then I have here, if I factor it out, 1 over radical n, I have e of the sum x1 plus dot 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 xn, right? Does that make sense, this part? And then I have the expectation of the sum is the sum of the expectations. So I have n of these e of x's, right? That's what that expectation is now. And then I have in the denominator radical n. And so here I'm just saying n is the same as saying the square root of n times the square root of n. And I still have my e of x. And then I have one copy of radical n in the two copies of radical n in the numerator, one copy of radical n in the denominator, and that cancels. That's where I get that leading radical n. Does that make sense? Any questions? Thank you for asking. All right. Because I remember when I was in your position, I used to hate when they would just say, here's this leap. I'm like, wait. How do we get there? So thank you. I appreciate your asking. Any other questions? And so I'm just using the algebraic properties associated with doing these expectations and these variances. Any other questions? Don't be hesitant to ask the questions, please. No? All right. Going once? Going twice? No? Okay. All right. Thank you for your question. And so what the central limit theorem says is that suppose you have a set of variables, set of measurements, I should say. It's the same x, so it's the same variable measurement. The 1, 2, 3, up to and including n just corresponds to the fact that you're taking a different measurement at a different time. And so if you had temperature, you have a thermometer, digital thermometer, interface to a computer, you take the temperature now, and then now, and then now, say, 10 times a second, right? So that's what this train of n many variables x means. And if these variable measurements, these measurements are so-called IID, stands for independent and identically distributed. And so the independent part means that the value of one measurement does not impact the decision of the other measurement. Okay, that's really important to the proof of the central limit theorem. And then the identically distributed talks about they're from the same distribution. And so let's say you have temperature and you're going to measure it outside in, what do you call it? The square, what do they call it now? The camera and the statue, red square? Red square. If you have a digital thermometer in red square and you're going to measure the temperature, you wouldn't measure it there and then bring your digital thermometer, say, to, somewhere in Boston and then assume it's identically distributed. It's not, because it's not the same normal distribution, because it's a different location. And so the requirement is, if you have n many measurements of the same quantity and it's independent and identically distributed, it doesn't matter what distribution an arbitrary measurement is from. If you have a finite expectation for the variable for your distribution and a defined variance, it's not infinite, then if you compute a transformation that involves a sum, it quote unquote converges in distribution to a standard normal distribution, or more correctly, to a normal distribution. And so what that means is, if you have the right version of a sum and you give it enough of those measurements in that sum, you can get any variable, regardless of distribution, to look like a normal. And that's what your central limit theorem says. And we'll actually see this on Wednesday with some data in a notebook to convince you that it really does work. And it's kind of scary that it does work. And so any variable from any distribution through a sum transformation can be converted to an equivalent normal distribution. And once it's a normal distribution, you can then transform it to a standard normal distribution. And now you can compare arbitrary measurements regardless of the distributions they came from. Does that make sense? Any questions? No? All right, we have about 12 more minutes. And so what this transformation is for the CLT version, just like we saw the transformation from the normal distribution to the Z distribution, instead of a variable, we have that transformation involving sum on the variable. So we have a term with our sum here. We have the expectation of that sum. We subtract from each version of the sum, okay? And we take that result, each one of those versions of the sum, and we divide by the standard deviation of the sum. That gives us the standard normal equivalent of that distribution involving the sum. Does that make sense? Any questions? And we'll actually see that on Wednesday in practice. So why in the world might one care about it? My wife works in an emergency room, and one of the things they do, if someone has arterial fibrillation, that means your heartbeat can be irregular. Instead of going wump dump, it kind of goes wump bump, 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 bump. And the reason why AFib or arterial fibrillation is dangerous is that blood can pool in, this is where my ignorance of biological things comes in. Blood can pool in the wrong chamber of your heart. And if it pools and not circulates, you can get some clotting, right? And that clot can break free and go to places like your brain, your legs, and it's a really critical, serious situation. But the problem with AFib, arterial fibrillation, is that it's transient, right? And so there's this thing called the Holter monitor, and it measures your heart rhythm, and you typically wear it for days, maybe 1 or 2 weeks up to a month, and it records your heart rhythm 24/7. And so what they enterprise to do is they analyze it, basically doing outlier detection. When does your heart rhythm become abnormal? Because it's transient, they need all of this data collected over time. So how do they do this outlier detection? Well, they don't just take your heart rhythm at a moment in time. They have a set of representations of your heart rhythm. They sample it over some window of observations, and they compute the average. Now you can take advantage of the central limit theorem, and you can do this outlier detection and also compare it to all sorts of other measurements. And so for this type of thing, the scheme is you take the expectation of the average, and then you take the variance of the average, and then how you do it from the data, you loop some number of times. Each time you take n many samples for some size n or window of observations. You compute the average, you compute the variance, and then you compute your equivalent standard normal version of this and do your outlier detection against new measurements. Does that make sense? Any questions? So the central limit theorem is immensely useful. Suppose you had customers coming into a store. Customer arrival is Poisson distributed, right? Events in time. So what do? Over some window of time, could be every minute, could be every 5 minutes. You observe how many events, how many people occur. You compute the average. You transform each one of these averages over 5-minute periods to the z-score equivalent. And now you can do things like correlation. So let's suppose you instrumented, for some strange reason, the heart rate of your employees. You could now say, what's the correlation of my employees' heart rate and the number of customers coming to the store? Are they under stress, right? You could absolutely measure that. Now, heart rate, it is normally distributed. Customer arrival, it's Poisson. How are you going to compare them? Well, you compute your transformation, may take advantage of the central limit theorem. You compute the equivalent z distribution, and now you can measure the correlation between those two z distributions, in spite of the fact that one started out as Poisson, which is discrete and deals in counts, and the other, heart rate, was normal, and it deals with, and you can transform that normal to a standard normal version. Okay, does that make sense? So it's an immensely useful tool if you want to make comparisons. But the process is to compute some transformation, and then you compute the z-score equivalent, and then with the resulting standard normals, you can make your variable comparisons. Okay. Another one, suppose you have a measurement of temperature, which is normal, and customers coming in to, say, an ice cream shop, right? And you want to see, is there some linkage between the temperature outside and the customers visiting the ice cream shop? Before central limit, you can't make that comparison. Now you can. You compute your transformation involving a sum for this Poisson variable, customer arrival. You do the same for temperature, which is normal distributed, compute the equivalent z version of the distributions, and now you can measure the correlation and using data say, yeah, I found that there's a moderate positive correlation with temperature and customers coming into the ice cream shop. So these are kind of examples just to show you the types of things you can do and why the central limit theorem is very important. Okay, any questions? Does that make sense? And when you first see it in data, it looks creepy, right? You could do it for employee stress. Now, I visited an Amazon fulfillment center because I was interested in the robotics. And there's a lot of stress in Amazon fulfillment centers, very high volume. And there have been efforts for Amazon fulfillment. I think in New York, it started employees to unionize, right? And so one could literally quantify stress by looking at core temperature, looking at galvanic skin response, how much moisture your skin, is your skin getting clammy, as well as heart rate. And you can absolutely look at the number of orders that are being processed, which is Poisson, versus these biometric measurements, which are normal distribution. So again, central limit theorem helps us here. And so why is the central limit theorem a big deal? It doesn't matter what form your distribution takes. It could be any of the discrete ones. It could be any of the continuous ones. We can make it into a normal distribution by transformation. And once they're on normal distributions, you apply your Z transformation to make it standard normal. And now you can make your comparisons. You can sort of take your kiwi fruit, turn it into an apple, take your orange, turn it into an apple, and now make apples to apples comparisons to be more casual in my parlance. Does that make sense? And when I first learned this and saw it, I didn't believe it. I said, let me try it with data, right? I was in the graduate statistics department at UMass, taking some courses, and I don't believe you. So I tried it. And it was kind of weird. It's kind of creepy and kind of wonderful in the same way. It really does work. Now, how big should N be, the number of samples? It depends on how complex your distribution is. And that's beyond the scope of this class. But it does work, and we'll see that on Wednesday. This is one of my favorite topics, but among topics. All right. Any questions? No? Does that make sense? So stay tuned. We have 5 minutes left. We'll just stop there till next time. On Wednesday, we will see this and some other things in Jupyter on Wednesday. All right. So have a great week, and I'll see you all on Wednesday.